Hi, Luke McKinney, Prep 101 Civ 100 instructor. In this video we'll look at 2 and 3 force members. They're the core of all structural analysis trust problems, and they're the key point that really saves a lot of time in any frame machine problem.
Two force members, what are they? Well, they're extremely useful in engineering is what they are. They're the basis of all the trust questions, and they save a huge amount of time in frame problems when they turn up because they reduce the number of unknowns in a problem. The basic rule, more unknowns, more problems. So how do we get rid of some of those unknowns? Well, a standard member, we have something that's pinned down at both ends. So this is pinned down at A and at B, and it might have a force acting on it. It might have a moment acting on it. So what are the support reactions on this member? Well, A is a pin. Now we saw before this has two unknowns, horizontal at A and vertical at A. And likewise at B, horizontal at B and vertical at B. And we can see we've got a whole problem here because we now have 4 unknowns. But we only have 3 equations. The sum of all the moments is 0. The sum of the horizontal forces is 0. The sum of the vertical forces is 0. So we'd need to go to other parts of the problem to get more information to solve it. And we can certainly do that. But if we have a special case of a two-force member, life gets a lot easier. So we always keep an eye out for these. A two-force member is so-called because it's only got the two forces acting on it from the ends. You just have A and B pinned down, and you have some conditions. It's pinned at both ends. It's only loaded at the ends, so there's no forces on the middle. That won't work. If you have any extra forces, they're just at the ends. And there's no moments anywhere. You can't have a moment on the middle. You can't even have a moment at the end. So you just end up with this basic, simple strut between two pins. And if you want, you can have some extra loads acting at those pins. Now, what does this give us? Well, the benefit is this means we have a two-force member, so we can replace the member with a single force. Just one force. And this force could be in tension. What does that mean? It means this member is just pulling on both its ends, like a rope. So you've got AB pulling up there, and AB pulling down there. And that's just like a rope or a cable we saw earlier. Or it could be in compression. The beam is being squeezed, and then it's pushing out at each side. So again, you just have the single unknown AB pushing out on each edge. But either way, you still only have one unknown. And that is way better than the 4 unknowns we saw earlier. So let's do a two-force member example, because if you haven't done an example, then you just haven't done this section. Engineering is all about actually doing these things and problems. The exam certainly is. So let's have a look at it. So we'll have a look at this here. We have a structure and we're asked to find the support reactions. And these are all massless beams with pin connections. So how do we do this? Well, we're asked to find the support reactions. So let's pretend we didn't know about two force members. A is a pin, so it has vertical and horizontal reactions. D is a pin, so it has vertical and horizontal reactions. And E is a pin, so it has vertical and horizontal reactions. And you can see, oh no, we have 6 unknowns. but we only have 3 equations. The sum of the moments around some pivot is 0. The sum of the horizontal forces is 0. And the sum of the vertical forces is 0. Only 3 equations. So we can only deal with 3 unknowns. This is very bad until we remember 2 force members. We always check for those at the start of a problem. And a 2 force member is pinned at both ends, only loaded at the ends. Now notice this means it must be massless. Otherwise there would be a weight load in the middle and no moments anywhere on it. And looking at that, we can see if we're looking for 2 force members, AB is a 2 force member, CD is a 2 force member, and CE is a 2 force member. So we can reduce all of those to one load acting along their length. So we do that. You see we've replaced AB, CD, and CE with a single force acting along the line between the 2 endpoints. So from A to B was 45 degrees. So that 2 force member load is now at 45 degrees. And we don't know whether they're tension or compression. Here, they're all holding the thing up, so I guessed compression, that they're pushing. It doesn't really matter. As long as you draw a clear arrow, the math will come out and tell you it's either plus in the direction of that arrow or minus against the arrow. Now, before you start doing math, always draw your axes. This helps avoid embarrassing mistakes, and it makes it a correct diagram. So let's start. The first thing we always do is the sum of all the moments. So we take the sum of all the moments around a pivot point is 0. What pivot point we choose? We choose the pivot point with the most unknowns, which we see as point C here. B has only one unknown, but C has 2. So we take the sum of all the moments around C is 0. So let's go through those. First, we have 20 newtons, a perpendicular distance of 2 minutes from C, and we can see that's turning counterclockwise around C, which is positive. Then we have AB, still a distance of 2 meters away, and now there's an angle of 45 degrees, sine 45, because remember, a moment is either the force times the perpendicular distance or the force times the distance times the sine of the angle between them. Now we see that's turning clockwise around C, which is negative. Then we move along. The next one, 10 newtons, a perpendicular distance of 1 meter away. That would be acting counterclockwise, which is positive. And then all the forces acting at C, CD, and CE, well, they're pushing on the door hinge, so they won't turn. Remember, any force pushing on the pivot produces 0 moment, equals 0. And lo and behold, beloved thing, one equation, one unknown. I'll put the answer here so we can keep everything on the same screen. That's AB is plus 35.355 Newton. That's positive, so it's in the direction drawn. So AB is pushing on B, so it's in compression. It's being squeezed and it's pushing out on the ends. So it's pushing out on B, and it would be pushing out on the ground at A as well. Then the next equation, do we do X or Y? Well, doesn't matter because both of them only have one unknown, but you do check that to see if one of them has fewer unknowns. Always do the fewer unknowns first. So the sum of all the horizontal forces is 0. So we've plus AB, the horizontal component to the right, minus CE's horizontal component to the left. One equation, one unknown. So we can find CE is 28.867 newtons. Again, positive. So it's in the direction drawn. We check our drawing. That was compression. And always write the word, or at least the letter C or T, compression or tension at the end, because you think you'll remember, but when you're running around doing a bunch of these, it's very annoying to have to double check or do something again. And then finally, the sum of all the vertical forces is 0. Well, we had plus the vertical component of AB up, minus 20 pushing down at B, minus 10 pushing down at the middle of the bar, plus CD up at C, and plus pushing up, always check your axes and words, the vertical component of CE pushing up at C. Again, that beautiful thing, one equation with one unknown, we find CD is minus 9.433 newtons. That's negative. So it's opposite to the direction drawn. We drew it pushing on C. It's actually pulling on C. So it's in tension. And that's all the forces acting on the member BC. Now we were asked for the support reactions at the ground, but that's handy enough because of two force members. The reason being that two force members just transmit the load along. Let's have a look. So I have AB. So we found AB was in compression, pushing up on B 35.355 newtons. Well, that means it's pushing out at the other end as well. It's pushing down on the ground 35.355 newtons. And then by Newton's third law, if the beam is pushing down on the pin at 35.355, then the ground and the pin must be pushing back up at 35.355 newtons. So you can see it's like this was transmitted along the two force member. It's basically a cable that can also push. So if we want to find the support reactions, and we do, because that was the question, then we can just plug them in. So the support reaction at A was 35.355 newtons along AB. The support reaction at E was 28.867 newtons pushing along CE, and D we found was in tension, so it's pulling. So DC is pulling up on D, it's pulling down on C. That's all internal, and so the ground must be pulling down at D to hold it there at 9.433 newtons, which is fun. Also, a little bonus element I want to point out here. It's not part of this question, but I've seen it trip people up on past exams, so I want to make it clear. Something about this diagram here. Notice how they've drawn A, D, and E on their own little bits of ground. That means you can't assume their level. I know A and D look like they're at the same level, but you cannot say that. If you were able to say that, you'd have a continuous piece of ground there, because you see that ground definitely doesn't line up with E. Maybe they accidentally are at the same height. If you do the math, if you're given distances, it might turn out, but just be careful. If they don't show here, if they don't show that they're on the same piece of ground, you just can't assume that. So that's a nice little extra tip there. Now, if you're interested, sometimes people want to know, why does this happen? We've already seen the big engineering part of it, the tool we can use, and that'll help us a lot. And more importantly, we did engineering example, because engineering without examples or exams is not engineering at all. It's just some words in a book. But sometimes people like to have an idea of the theory. Why does this happen? And it works out pretty nicely. The core idea here is equilibrium. Everything adds up to zero. Sounds like a very negative lesson, but very useful when you're building bridges and towers. The moments add up to zero, and the forces add up to zero. Now, if you just have some object with a lot of different forces and unknowns acting on it, you can work them all out. They all work out balanced. The equations solve. There's a lot of different ways to make that possible. But if you have only two forces acting on an object, then they must be equal and they must be opposite. Otherwise, the forces wouldn't add up to zero. If this is 10, the other must be 10 in the opposite direction. Otherwise, they simply can't add up to zero. Also, they must be in exact line with each other. Otherwise, the moments won't add up to zero. For example, if we look at it here, if that 10 was equal and opposite but not in line, now you see, even if the forces cancel out, it'll start spinning the object, so the moments don't cancel out. So if you have only two forces acting on something, they must be equal and opposite and in line. The case for us is the idea of a pinned beam. If we have something pinned at A and B, if there's other forces and moments acting all around that, then yeah, the forces at A and B can be in any direction, A and B. And then we break those up into the usual vertical and horizontal components. So you can see BY and BX, AY and AX can be anything. We have 4 unknowns, which is a lot. But if we only have pins and loads at the end, so there's no other forces, there's no moments at all, we now only have 2 forces acting on this, A and B. So they must be equal and opposite and in line with each other. So we just give them a single name, AB. So it's either in tension like this, pulling on both ends, or you could have a situation where the beam is being squeezed and then the force is in compression, pushing out on both ends. Sometimes people have a bit of worry seeing that. It's like, hang on, compression, but it's pushing out. Remember, it's just like if you're standing there and you're leaning on a post, you're compressing the post, you're pushing down on it. So it'll be pushing back out on each edge. So something in compression, by Newton's third law, is pushing back out against that compression. And this two-force thing leads to one cute thing. Notice we see there, these forces must be in line between the 2 pins. It doesn't actually matter what shape the beam itself is. So if I had A and B, and I had some weird convoluted shape of single fixed beam, it doesn't matter what shape the beam is. I know the forces at A and B, the 2 forces, must be equal and opposite and acting only along the line of the beam. Which again, something, if you see a very weird looking beam on a question, will make you think, well, hang on, do I really need the shape of that beam at all? After 2 force members, which are hugely useful and turn up everywhere, we have 3 force members, which are a little novelty that we just have to briefly look at. Like, this isn't like NBA or FIFA games. Adding the number to 1 doesn't mean we can sell it for $60 all over again. This is only a slight novelty, but it's on the course, so we do want to make sure we know it. The core, the keyword, the heart and soul of this course, as always, is equilibrium. All the moments add up to 0. All the forces add up to 0. Now, if we have an object with only 3 forces acting on it, there's only two ways that can happen. One way is if all the forces are parallel and anti-parallel, and they're exactly balanced. So for example, you might have 10 up, 5 up, and 15 down. That way, the forces all cancel out, and because they're all pushing along the same axis, the moments cancel out to 0. For any other situation, if you have just 3 forces acting on it, and it's in equilibrium, the 3 forces must be concurrent, which in this case exactly means they must all cross at one single point. Because that means, well, you can see if I took the moments around that point, the total moment would be 0, because all the forces are pushing on the pivot. In the same way, a force pushing on a door hinge won't give us a moment, it won't make the door turn. Now that's not usually true. Normally, if you have 3 forces just hanging around, you can see 2 of them will cross at one place, and then a different place, then a different place. So normally you don't have this special effect, but for equilibrium, the 3 forces must all be concurrent, because that's the only way you can stop them from rotating the object, giving it an angular acceleration, and then you're not in equilibrium anymore.
I hope that was useful. There's plenty more videos in the playlist, but what's even more useful is lots of exam examples and exam specific advice. And that's what we do in the prep sessions. So join the Prep 101 Study Hub Facebook page to find out when those go on, and many of them are even free, so you definitely don't want to miss those. Hope to see you there.